Today we're going to start off with an old problem and then see what this old problem can tell us about new stuff that we need to do. Let's find the equation of a line tangent to 4 minus x squared when x equals -1. So we know the process for this. We need to find the slope and a point. That's what we need to find the equation of a line. So we need a point and a slope. This is because lines are very simple objects. They just need to start somewhere and a direction to go. So that's all we're looking for. We need a place to start and a direction to go. So the point is the place to start and the slope is a number that encodes the direction to go. That's why linear algebra is such an easy class, because everything is flat. We need a place to start and a direction to go. So that's all very simple. So the point, we have half of a point already when x is equal to -1. So we'll find f of -1 is 4 minus a -1 s squared. And so it's going to be 4 minus 1 is 3. So we have a point already. Point is -1, 3. Now the next thing that we need is a direction to go. So for that, since this is calculus, we get to use the derivative. So for our direction to go, we'll take the derivative f prime, which will be minus 2x. And then the slope will be f prime at -1. So the slope is f prime at -1, -2 times -1, which is 2, last time I checked. I was double checking my calculations with my calculator earlier. I'm not very good at arithmetic, so I'll use a calculator to double check things. So here, now we can write the equation of the line. So our equation, I'm just going to call it y, is going to start off at the point 3. And we're going to go in the direction of +2 whenever x is different than -1. So I'm going to write x minus a -1. So this is the way that I like to think of lines. This is how I'm writing the line, but this is the way we like to think of the lines. We're starting off at 3 when x is -1, and we add 2 a bunch of times. That's what lines do. We start off with a number, and then we add the slope a bunch of times. Start with b, add m a bunch of times. I know we typically write them mx plus b. I think that's terrible. It really doesn't matter, but I think that's terrible because the line should start at b and add m a bunch of times, where the x represents a bunch of times, m represents the direction, and b represents where things start. Since b represents where things start, we should just start with b. Now, I'm willing to bet most of us did not write this line. Most of you wanted to do some extra calculations because you like risk taking, and you want to risk making some minor mathematical error that tanks your whole problem, and you wrote this problem in slope-intercept form. So what's the intercept? Is the intercept 5? Yeah, it must be 5. So you probably wrote y equals 2x plus 5. Show of hands, who wrote 2x plus 5? Whose indoctrination is so strong that you only write mx plus b? This is what's happening near x equals 0, and that ain't got nothing to do with what I'm asking about. I'm concerned about what's going on with -1, not way over at 0. So I'm just making fun. It truly doesn't matter. But the thinking what I really want to emphasize is more about thinking. So when we write 2x plus 5, that's the standard way that we write lines, mx plus b. It's exactly the same to write 5 plus 2x, but I think this, reading from left to right, reveals more about how we structure a line. It says start off at 5 and add 2 a bunch of times. That's the way I like to think about this form. So y starts at 5. Y is 5 when x is 0. And y increases by 2 every unit. We start at 5 and add 2 a bunch of times. And notice that the multiplication is just repeated addition. So adding 2 a bunch of times means we can multiply the 2 by x, the number of times we're adding 2. I just happened to do the problem over here in a point slope form. So this would just be y is 3 when x is -1. When we're adding 0, when the x plus 1 is equal to 0, we're adding 2 0 times. So this just says y is 3 when x is -1. And we still add 2 a bunch of times. And that's what gives our linear function that flat linear look. Any questions? I see Jonathan has a hand up. Oh, I think I said show of hands. All right, so this is a very straightforward problem, but we need to update this to a multivariable calculus problem. And so we want to make sure that we're not just going through motions of plug in the value, take the derivative, plug that in, and then mechanically put things together. We want to make sure that we have thinking in place so that we think about, so that we're thinking correctly about linear functions. Start at a place and add the slope a bunch of times. All right. Let's next take a look at the direction that we get from the derivative, specifically the slope. We know that we think of the slope as the rise over the run. So a lot of times when we're finding the equation of a line, we think of it as we need to find two things, a point and a slope. But the slope contains two pieces of information, a rise and a run. So the slope contains two pieces of information, a rise and a run. So let's think about the slope as a direction. So I want to think about the slope as a direction. So the slope contains two components, the rise and the run, the change in y over the change in x. So when we have a slope, we think of the rise over the run, and that's the change in y over the change in x. So there's two components to the slope. So for example, when we write a slope of 2, we're writing a ratio of the change of y to the change in x. So for example, if m is equal to 2, we think of that as 2 over 1. So we think of a delta y as 2 and the delta x as 1. We add 2 whenever x increases by 1. That's really what the slope is telling us. What happens to y when x increases by 1? So we can draw a picture of our, let's see, we have 3 plus 2 times x minus a negative 1. And so there we have our tangent line. So I wanted to draw on this, so I'm going to need to draw a picture of it anyway. I can get away with not drawing it. So we had the point at the point 3, 1. At the point 3, 1, we had a change in y of 2 and a change in x of 1. So there's a rise of 2 and a run of 1. And so that's how we get another point on the line. So there are 2 components to the slope. We summarize it with one number, but the slope has 2 components, an x and a y. How much y changes with respect to x? There are 2 components to the slope. The rise or the change in y, and the run or the change in x. Any questions? All right, so nice, simple problem. Everybody loves find the equation of tangent line. You were happy to see that one on a final exam because you know this one. Take the derivative, plug in the points, plug the point into the function, put them together into the equation of a line. Any questions, comments, snide remarks? So what we want to remember is that when we have a function of x, when y is a function of x, we have a function of one variable, we get a one-dimensional curve in two-dimensional space. So when we have a function of one variable, function of one variable, oops, I forgot to say the graph of. The graph of a function of one variable is a one-dimensional curve in two-dimensional space. With y equals f of x, y is the height of the curve above the point x on the x-axis. So y equals f of x means that the height of the curve above a point x on the x-axis is given by the function. And that's why we end up with a one-dimensional curve. Because we're plotting the height over one dimension in our two-dimensional space. So now we need to upgrade all this to a function of two variables. That pause was not intended to be dramatic. That pause was just in case people are copying notes. Like in-person class, I could see when people are copying notes. But with 37 people in the room, I think like half of them just kind of like wake up, log in, and then go back to sleep. It's like, oh, professor doesn't require video to be on, I'm going back to bed. And really, I think computers are sophisticated enough that if you just record yourself supposedly paying attention, you could play that on a loop. I've seen a heist movie before. I know how this works. All right. So we know that a function of one variable, the graph of a function of one variable will be a one-dimensional curve in two-dimensional space. So the graph of a function of two variables say z equals f at xy, will be a two-dimensional surface in three-dimensional space. All the points on this surface, everything that satisfies this function has an x, y, and z. That's why we know it's three-dimensional space, because the points are all the form x, y, and z. It's a two-dimensional surface because a function is only going to return one value. And so z will be the height of the surface above any point xy in the xy plane. That's why we're getting a two-dimensional surface, because at each point xy in the xy plane, we're getting 1 point. So z is the height of the surface above each point xy in the xy plane. So a good question came up in the chat: when do parametric equations come into play? Now notice that we're in three-dimensional space, and with a function we'll describe a two-dimensional surface, but that's not the only thing that we can describe in three-dimensional space. With 3 dimensions to work with, we could also have a one-dimensional curve running around in three-dimensional space. And at that point, we're going to want to use parametric equations to describe the coordinates of a single point, rather than a height above every point in the XY plane. So great question. As we start off with three-dimensional space, the stuff that we could fit in there is two-dimensional surfaces, which sometimes we can describe with a function. But we also would want to describe a one-dimensional curve in three-dimensional space. Say the path of a fly flying through my kitchen right now, sort of distracting me. Not that it takes much to distract me. So good question. That's when we're going to need parametric equations. So we have the graph of a function of two variables is going to be a two-dimensional surface in three-dimensional space. So now instead of drawing a tangent line, instead of finding the best, when we draw the best linear approximation of the surface, instead of describing a line, we're going to want to describe a plane, which is a linear function in three-dimensional space. I keep wanting to say R3 because I just got through doing the linear algebra course. So if you hear me talk about R3, that's three-dimensional space. So we want to do the same thing that we did with the tangent line. We want to find a tangent plane. So now we want to upgrade the tangent line problem. Whereas before we had find the equation of the line tangent to the curve. We're no longer dealing with a curve. So instead of a line tangent to the curve, we're going to have a plane tangent to the surface. So there's the problem in R2, find the equation of a line tangent to the curve. And here's the same problem in R3, find the equation of a plane tangent to the surface. In R2, the equation of a line, a linear equation gives us the equation of a line. That's not a big shock, that's where the name comes from. But in R3, the linear equation will give us the equation of a plane. So the equation of a plane in R3 the equation of a plane is going to be our linear equation in three variables, whereas the equation of a line is a linear equation in two variables. We get a line when we have y and x, and if we have x, y, and z in a linear equation, we'll have the equation of a plane. Any questions? So we're going to need to describe, when we want to describe a line, we know we need a place to start and a direction to go. So remember that the equation of a line has a place to start and a direction to go. We need a place to start and a direction to go. When our place to start was a point, x naught, y naught, and our direction to go was just one number, the slope, we wrote the equation of the line as, let's say, y is y naught plus m times x minus x naught. And we know that the slope m is the ratio of the change in y to the change in x. M is how y increases when x increases by 1. So m is the slope. The change in y divided by the change in x. It's what's happening to y when x increases by 1. And it's a ratio. That's why 10/5 is the same as 2 over 1 or 100 over 50. The amount of change is not important as long as the ratio, we maintain the same ratio. That's what keeps the line flat. So so what we're going to find is that when we want to find the equation of a plane, we're going to want the same things. So let's think about what we'll need for the equation of a plane. So the equation of a plane should want similar stuff. In this case, our place to start is not going to be a point x naught and y naught. It'll be a point x naught, y naught, and z naught, because we're in R3. I'm already doing the R3 thing, so I hope you get used to things quickly. A place to start which will be just some point in R3, say x naught, y naught, and z naught. But when we're standing in a plane, we don't just have one direction to go like when we're on a line. On a plane, we can go left and right, and we can go forward and backwards. So what we're going to want for the equation of a plane is two directions to go. A left-right direction and a forward-backward direction. Oh, I went left-right, so I'm going to go backward-forward direction. So the equation of a plane is going to want the same stuff, a place to start and a direction to go. But since we're standing on a plane, and a two-dimensional plane, and not a one-dimensional line, there are two directions that we can assign. There's an infinite number of directions because we can face any direction. But we're going to break it down into components, a left-right direction to go and a backward-forward direction to go. So we're not going to have one slope, we're going to have two slopes. We're going to have a change in, and the most convenient thing for us to do, we're going to look at how z is changing in the x direction and how z is changing in the y direction. The main reason that we're doing this is that, once again, we're describing surfaces with functions where z is a function of x and y. So our equation of the plane should be solved for z as well. So we're going to have a change, a left-right direction to go. Let's give that a name. Let's call that m. We were able to get away with describing it with one number before. And so let's come up with a similar name for our backward-forward direction to go. I'm going to call that n. So that's going to force me to enunciate since I have an M and an N. I should have used P and Q. Oh, well. It's like we want to use different letters to represent things. It's really inconvenient that most of our letters rhyme. Anyway, so let's see if we can structure the equation of a plane using in the same way that we made the equation of a line. Z is going to have a place to start. The y naught is like the starting value of the equation of the line. When x is equal to x naught, we don't add m at all. We just start off at y. And we're going to do the same thing for the equation of a plane. So I'm going to start off saying z equals, and I'm going to say z starts off at z naught. Remember, I need a place to start, and the value of z to start is going to be z naught. That's the point that's definitely on the plane. Then we're going to have our left, right, and forward, backward directions to go. So we're going to add m a bunch of times in one of our directions. Let's say we're adding m in the x direction. But that's only one of our directions. So now we'll need to add the n in the forward backward direction. So now we'll add n in the forward backward direction. So now at the point x naught and y naught, we have added m and n 0 times to z naught. And then when we can see that when x starts changing from x naught, we start adding m. When x is x naught plus 1, we add m 1 time. When x is x naught plus 2, we add m 2 times. So the m represents how z is changing in the x direction, the way I've written the equation here. And over here in this term, n is how z is changing in the y direction. When y is equal to y naught plus 1, we add n 1 time. So if we change x by 1 and y by 1, then we add m 1 time and n 1 time to the value of z. And that's how we get the height above the xy plane. So in the equation of the line, m was how y was changing when x increased by 1. But now I have m and n, where m is how z is changing when x increases by 1. And n is how z is changing when y increases by 1. So m will be the change in z with respect to x. That's what we add to z when x increases by 1. And n will be the change in z with respect to y, what we add to z when y increases by 1. So following a similar setup here, that's going to be the change in z. dz dx, or delta z over delta x, is the change in z when x increases by 1. We're using z as our focal point because we're starting off looking at functions of 2 variables. So we want things in function mode. X won't always be left and right, and at Y always forward and backward. I just needed to imagine us standing on a plane and know that we can move left and right and forward and backward. We got W, A, S, and D. So we've got A and D to move us left and right, and W and S to move us forward and backwards. It's weird that I still refer to it as W, A, S, and D, even though when I was, the last time I played a game that required those was World of Warcraft, and I had to shift that all over to R, D, F, and G so that my pinky would have access to Q, A, and Z to activate things. So, but I still say W, A, S, D. Any questions? All right, so notice that we go back to our original problem. We were where we wanted to find the equation of a line tangent to a curve. We had to have a point, and then we had to have a slope. We needed a place to start and a direction to go. When we upgrade that to find the equation of a plane tangent to a surface, we still need similar information, a place to start and two directions to go. How does Z change in the X direction, and how does Z change in the Y direction? We need to know how Z changes in each of those directions. Any questions before we turn the page, since we're out of space? So that's a great question. You think you could see a pattern to add one more dimension. So what if instead of in R3, we were in R4, and Z was a function not just of X and Y, but also of a third variable W? What would happen? What would our linear equation look like then? Add another direction and another start with W naught. That's exactly what we would do. So MN, then there would be a plus P times W minus W naught. So that would be how things are changing, how Z is changing in the W direction. This is why we like linear functions, because we can describe the changes very simply. It's always doing the same thing. So unfortunately, it's hard to draw what's going on because I only have 2 dimensions to work with on my pad of plastic. But if we think, if we draw a plane, let me draw a plane above, let's say, I'm going to put the origin here. I guess traditionally, left, right is the Y, and then X is forward and backwards because it comes out of the paper. So above a point, let's say X, Y, so X naught, Y naught, and Z naught. We're going to look at how, we're going to look at how Z is changing in the X direction and in the Y direction. So we're going to have 2 different slopes. M, which was the slope in the X direction, and N, yeah, this is why I usually don't draw this, and N will be how things are changing in the Y direction. So drop this down here. That's what happens when y increases by 1. We can see z change its value. And if we drop this down, this point down to the plane, we can see how things are changing in the x direction. So those are where the delta x and the delta y happens. And then over here on the xz plane, over on the xz plane, we'd be able to see how much z has changed. So this raises an important question. We want to find the equation of a plane tangent to a surface. We know we need a place to start, and we need directions to go. An x change in z over with respect to x, and a change in z with respect to y. We know that in Calc 1, we learned we take derivatives to find those. So we're going to have to update our derivative taking skills to find the derivatives, the two derivatives that we need. So let's talk about where derivatives show up. Now, we're going to talk about derivatives of functions of two variables. And for those of you who read along ahead in the books, like, oh, dude, this is not till chapter 14. What are you doing to us? We're not ready. And my hypothesis is you already know what you should do. So we need to be able to find derivatives. When we have a function of two variables, we want to think about where do derivatives show up. Once I started saying things like change in z with respect to x and change in z with respect to y, that should make you start thinking derivatives are about to show up. That's like revealed in the trailer. That's not even foreshadowing. Just watch Fast 9, the greatest movie franchise of all time, Fast and the Furious. And in Fast 9, they had this shot of, well, everybody knows it's John Cena, so this is not a spoiler. John Cena shows up, but they showed him dramatically from behind as if we're not supposed to know that it's John Cena. But we all know that it's John Cena. Just show us his face. You showed him in the trailer. We know the whole story from the trailer. But they had this dramatic shot of John Cena being ominously shot from behind as if we didn't know who it was. You know what I mean? It's like, oh, dude, we saw this in the trailer. Also, if you might want to mute me for a second, because here's another spoiler, but it was a spoiler that was in the trailers. We also find out that Han is alive. Now, if you don't know who these people are, that's just because you're not well versed in the greatest movie franchise of all time, Fast and the Furious. And that's okay. Knowledge about the Fast and the Furious franchise only comprises about 25% of the final exam in this class. So you'll be fine. You'll still be able to pass. I'm just kidding. It's like 35%. You won't be able to pass. I'm just kidding. It's 100% Fast and the Furious trivia. I'm just kidding. That's not trivia. This is important cultural knowledge. I'm just kidding. There's no Fast and the Furious information needed to pass the final. What are we talking about? Oh, yes. So once I started talking about things like the change in z with respect to x and change in z with respect to y, you knew that derivatives were going to show up. Once I started talking about equations of tangent things, you knew derivatives were going to show up. For a function of two variables, we need two directions. For z is equal to f at xy, we need two directions. We need how a change in z with respect to x and a change in z with respect to y. So that means that we're going to need to learn how to find a dz dx and a dz dy. The good news is you already know how to do it. I'm going to put up an example of a function of two variables, and you're going to tell me how to find dz dx and dz dy. I'm going to make sure my Jeopardy theme is queued up. So let's say, for example, so the good news, y'all already know how to do this. Oops. So the good news is y'all already know this. Let me write down a function. Let's say that z is going to be 2x to the third, y to the fifth. I need two directions, a dz dx and a dz dy. How am I going to find, what's my dz dx? What's my change in z with respect to x? I called that m before. And we'll also need a dz dy. What do you think my dz dx should be? We haven't talked about how to do this. I want you to guess how it might work. I want you to propose something that we can use to find the dz dx. I haven't given you a point, so there's nothing to plug in. 6x squared is a good part, but what happened to the y? I like the 6x squared parts. And we'll keep the y to the fifth. So there seems to be consensus that we'll have the 6x squared and we'll just keep the y to the fifth. What about dz dy? Let's follow that same pattern and guess what we would use to find dz dy. We'll have a 10y to the fourth, and then just keep the x cubed. So 10 x cubed y to the fourth. So we didn't have any instruction on this. I just said, you know, it's still derivative stuff. And so we just applied derivative thinking. The derivative of z with respect to x, we just keep y as a constant. Y is just a constant multiple. We're imagining y to be constant because we're caring about what's going on in the x direction. And for dz dy, we hold x constant and look at what's going on in the y direction. In this case, we don't need the product rule because x and y are not functions, are not separate functions of a common variable. We need the product rule when you have a function of x multiplied by another function of x. Here, x and y are both the variables. So this first one is the partial derivative of z with respect to x.
Professor.
So this first one, one sec. This first one is, we say, is the partial derivative of z with respect to x. We take the derivative with respect to x and hold y constant. And then over here, 10x cubed y to the fourth will be the partial derivative of z with respect to y. We're holding x constant. Question?
Yeah, you said it's a partial derivative, right? Is it the one that writes there's a special D. It's not
Yes.
it's not the Latin D. I think it's Cyrillic D.
Yeah,
it goes backwards.
We use the backwards, a backwards 6 written upside down. That's the D that we use for the partial derivatives. We'll go over notation soon because, of course, there's notation. This is a math class after all. There's notation for all kinds of stuff. But the concept is we want to know how the z is changing in the x direction. So we get to think of y as just being a constant. So I think of y to the fifth as just some number. And then when we look at the partial derivative of z with respect to y, we think of x as constant and take the derivative with respect to y. So in the first one, we did a 3x squared times 2xy to the fifth. And in the second one, partial derivative of z with respect to y, we did 5y to the fourth times the 2x cubed. So it works pretty much how we expected it to work. That's why Calc 3 is so simple. We already know how to do the stuff. We just have to adapt it to functions of more than one variable. Any questions? Incidentally, it's totally okay if that was not your guess, because other things like the product rule, those are perfectly reasonable things to think about when you're looking at this problem. I didn't tell you how to do this problem. I just said guess. I like to do that a lot because guessing is really the only thing that we ever have when we're faced with a problem. We just have to guess how things should work. Any questions? Comments? Snide remarks? All right. One of the reasons that I like to do this problem on the first day is that I want you to all to recognize that the most important thing to do anytime you're faced with a problem is something. The most important thing that you can do when you're faced with a problem is something. You have to try something. You can't win if you don't play. Then you just have to be ready for that thing to be wrong. And then if that thing is wrong, if you can't see why it's wrong, you just go back and try something else, or you start speculating on why it's wrong and start making adjustments. So a lot of times we'll be looking at a problem and we won't know what to do, and that keeps us from doing anything. So we always talk about flight versus fight responses, but we always forget one of the most common things to actually happen, and that's freeze. There's fight, there's flight, and there's freeze. And that happens a lot when we're dealing with math. We're faced with a problem, we don't know what to do, so we don't do anything. So the most important thing that you can do when you're faced with a problem is something. I will never make fun of you for what you try. I actually don't make fun of you for freezing either. Okay, maybe a little bit. But I don't make fun of you for having those reactions, because those are natural reactions. And I also don't blame you for freezing in the face of a problem, because you've been subject to several years, let's just go with the nominal 12 years of mathematical psychological warfare, where you were made to feel bad for being wrong. And that whole time, we should have been celebrating all those times that you got things wrong. We shouldn't have been marked it off with a red pen and said, you're bad at this for being wrong. We should have said, hey, that's a guess. You did something. The most important thing to do, you did something. we should celebrate that, and then go back to the drawing board and say, let's try something else until we get something that works. Because that's the only way we're ever going to make progress. But the way that we do math in this society, the way I use the term loosely, teach math in this society is very punishing and psychologically damaging. And it makes it, and is very discouraging of doing things like guessing. Because we forget that the only thing that we ever had when we were building math, like I was there, is guessing. Coming up with rules and saying, does this rule work? No, that doesn't seem to work. Nope, that either. Nope, not that. Nope, not that. Ah, this one will work. That makes sense? So when you get stuff wrong, you should be happy. It's like, oh, I'm incorrect. I have an opportunity to learn something. If you get everything right the first time through, you should be sad. You're like, oh man, I don't get to learn anything here. Apparently I already know this. Bummer. You know what I mean? But I totally get it. I totally get why you freeze, because you have been trained to be afraid of being wrong. Don't be afraid to be wrong. Be wrong boldly. But when you're wrong, say, oh, yeah, that didn't work. Let's try something else. That's it. You know what I mean? Don't vote for me in 2024. I don't want to run for office. You don't want, okay, so here's why you don't want me to be in office. As a teacher, especially as a teacher in community college, I have essentially absolute authority in the classroom. If everybody in the world thinks that you should get a B in this class and I gave you a C, guess what grade you're getting? That's absolute authority. You can't take someone that's used to having absolute authority in their domain and give them a bigger domain. It would just end badly. You know what I mean? I would turn into the emperor. I'd start doing some shenanigans behind the scene. I'd start wearing a hoodie more often. One of you would become my apprentice, but you wouldn't be my apprentice, you'd be my apprentice. And I would do this a lot with my fingers. So it would be a bad idea. You know what I mean? Join the calculus side. Together, we will rule the galaxy. Or at least calculate some things about it. All right, that's going to do it for today. The things that you should be working on. I've put up assignments in chapter 12. That's ostensibly our starting chapter, even though this class started a long time ago. But start with working on the problems in chapter 12. They have a nominal due date of August 29th. The problem should be set up so that you have unlimited attempts. So that's to encourage you to keep going until you get the problem right. Also, to circumvent Wiley's numerical answer thing where it's like plus or minus 2%. And if you have a tolerance of plus or minus 2%, sometimes that means you have to have exactly the right answer. So good job, Wiley, not understanding how percents work. I'm just kidding. I clown on Wiley all the time, but it's a perfectly acceptable product. I mean, I'm using it. So, all right. That's going to do it for today. Tomorrow, we'll talk more about not necessarily partial derivatives, but definitely how we describe things. All right, that's going to do it for today. I will see y'all on Monday, because today's Thursday. So if you have questions, this is our first Thursday, so I have to do this part as well. If you have questions, send me an email, and I have time tomorrow morning, and we can set up a face-to-face if we need to, if we can't get things sorted out through email. So first line is email. Second line is setting up a face-to-face during office hours. If you can't make office hours from 9 to 11, then we could try to work something out. All right, now that's it for today. I'll definitely see y'all on Monday. Everybody have a good weekend, and thanks for playing.